Namaste and welcome to this lecture on mathematical foundations for machine learning. We have been looking at the idea of probability, random variables and stuff, and in the last couple of classes we have looked at the joint moments of discrete random variables and so on. We tried interpreting a lot of interesting things there. We looked at the idea of covariance and all those things, but one thing that we did was we did everything with respect to the discrete random variable. You have the continuous random variables too. You can have jointly distributed continuous random variables, in which case you will have your joint probability density function, which we have seen already. Only thing that we have not seen is the joint moments as far as the continuous random variables are concerned. We will just have a quick look at it and then we will go ahead with the idea of conditional random variables and so on, right. So, we will just quickly have a look at the joint moments of continuously distributed random variables. So, that is the focus of this lecture today. We will look at the joint moments in the case of continuous random variables, followed by conditioning of random variables, because this conditioning of random variables is also pretty essential or pretty important as far as your machine learning is concerned, where you do for every class you have like multiple features and then you say that I have these features. So, what is the probability that this belongs to this class? So, given that I observe these features, what is the probability that it belongs to this class and so on. We will be looking at that. And so, we need to look at conditioning of random variables too, right. So, we will look at both of them in this lecture. So, the first thing that we are going to do is we are going to look at joint moments of continuous random variables. Joint moments of continuous random variables. One most important thing that you need to do is like I mean whatever you had in terms of discrete is available in terms of continuous, jointly continuous random variables also. Just that in case of discrete we did the summation because they were all like probability mass functions. So, you have to do a summation over there. In this case all we need to do is we need to replace those summations with integration. So, what we want to do is I want to look at expected value of let us say x power I y power, okay, let me say x power m y power n. X power m y power n, where okay we will say x and y are continuous random variables with joint PDF given by f x comma y of x comma y, right. So, this is what we have. So, I want to find out the expected value of x power n y power n. This is basically given by integral minus infinity to infinity, integral minus infinity to infinity x power m y power n f x comma y of x comma y dy dx. Now, you can list out the same kind of moments that we did in the case of discrete. Just put m is equal to 0 and n is equal to 1, you end up getting integral minus you have integral minus infinity to infinity, integral minus infinity to infinity y power 1 f x y of x comma y dy dx. So, you end up getting expected value of x. So, I will say m is equal to 0, n is equal to 1, implies it is expected value of y, then m is equal to 1, n is equal to 0 is expected value of x, and m is equal to 1, n is equal to 1 is expected value of x y, which we called as correlation, and we also have expected value of x minus mu x into y minus mu y, where mu x and mu y are the respective means of x and y respectively. right. So, we have this and this is what we call as covariance of x comma y, which is given by expected value of x minus mu x into y minus mu y. This again you can get it in terms of your integral, which is nothing but x minus mu x into y minus mu y into f x y of x comma y dy dx. So, that is going to give me my covariance of jointly distributed random variables, continuous random variables, right. Okay, great. So, all the other properties hold good here. You can look at correlation coefficient, you can look at all that. So, everything holds good here, right. So, now what we do, having studied pairs of random variables, their joint probability density functions, joint probability mass functions and so on. Now, what I want to do is I want to get to the notion of conditioning, because when we did events, when we were talking about events and when we looked at two events on the sample space, let us say A and B, the probability of A and B happening together was given by the probability of A intersection B. When you look at the joint probability mass function or the joint probability density function, that is exactly like what we had in terms of our events. Let us just have a recall of the definition of joint probability mass function. So, I have p x comma y of x I comma y j, we had this, which is nothing but probability of x equal to x I intersection y equal to y j. This was the probability that we had. That means, the joint probability mass function that we have here itself is like basically the intersection of two events, where the event is x equal to x I and y is equal to y j, right. Similarly, you can look at our joint probability density, you can look at joint probability density function and you can write the probability in terms of the joint probability density function. So, that is basically the intersection of two events. Now, the moment we start talking about two events, we want to look at what is the update that one event is going to give upon the occurrence of upon its occurrence. So, we want to find out what is the information that I get about an event A knowing that event B has occurred, and that is precisely where we got into the notion of conditional probability, right. We had conditional probability, we had this idea of conditional probability which said P of A given B is nothing but P of A intersection B divided by P of B. This is what we have, right. So, what is this conditional probability P of A given B interpret to? It is basically the probability of an event A given that we know that some other event has occurred. What is that some other event? That is basically event B. So, what do we say? We say that given, so this is nothing but, so this probability is nothing but the probability of event A given that we have an information, we know that some other event B some other event B has occurred. Now, in essence, what are we saying? We are saying that look, the knowledge that event B has occurred, does it improve our knowledge or does it improve or does it improve the knowledge that we have about another event, say let us say A. That is what we look at. Okay. Now, we already know that if A and B are independent, this update is not going to happen at all. So, let us write that also. If A and B are not independent, then the knowledge of B or event B having occurred, will definitely change, will change the probability of A. Right, it will always change. So, we know that okay, there is somebody who is carrying an umbrella. Now, we know that look, this guy is carrying an umbrella, therefore, there could be a slight chance that it might rain. That means somebody carrying an umbrella is going to give us some input or some let us say insight into whether there is a rain or not, right. Okay. So, what we have is, let us reinterpret, let us interpret this P of A given B again. We are going to say P of A given B this is the new probability in the light of additional knowledge. What is that additional knowledge? The additional knowledge is event B having occurred. Right. Now, let us just take a quick case study. Let us see, like let us take a simple example and see if you can understand this idea. So, what I am going to do is I am going to consider an experiment. So, let us say this, consider the following experiment. What is the experiment? There are two coins. There are two coins, let us say coin 1 and coin 2. One of which is fair and the other is biased. Now, what do? We have two coins of which one coin is fair, that means equal chances of getting a head and or a tail, and then I have a biased coin. We do not know which is it favoring most of the time. So, we will just say biased coin. Now, what we have is this biased coin, this loaded coin, we have these two coins here. What we are going to do is we are going to pick up one of the coins randomly and then toss that coin 5 times, right. So, what you do is let us write this, you choose a coin randomly, you choose a coin at random and toss it 5 times. So, the question here is what is the probability, what is the probability of observing more than 2 heads. So, the question is very clear, it says I have a fair coin and I have a biased coin. Now, what I do is I choose one of these two coins at random and toss it 5 times. What is the probability of observing more than 2 heads? Let us take it for example, let us assume that okay, there is one coin which is fair, that means it has let us say head and tail, and the other coin is biased where we are going to have both sides of the coin to be head. Now, if I choose coin 1, there is a fair chance of getting a head or a tail, and if I choose a coin 2, at all times I will get head only, right. So, what it says, you choose a coin at random and you toss it 5 times. The question is what is the probability of observing more than 2 heads. Now, one thing we need to understand, if you carefully look at the problem, we need to understand that the number of the first thing that you do is you choose a coin and then you toss the coin, which means depending on what the coin is, which coin you have chosen, you are going to have your probability to change, probability of observing more than 2 heads. For example, if you choose the biased coin, let us say the coin with 2 heads, you toss the coin, anytime you are going to get only heads, right. It is a sure shot event that we have, because both sides are going to be heads. Whereas in the other case, the probability is being, the coin is fair, it says the probability of head is equal to the probability of tail is equal to half. So, you are going to have the probability to change. In this case, it is always going to be 1. Now, what we do is, how do we answer this question? Therefore, to answer this question, first of all we must know what coin we have chosen, right. So, to answer this question, first we need to know which coin was chosen. Now, the moment you have chosen the coin, now I want to figure out the probability distribution of heads, like which is more than 2 heads that I have. That means, given that I choose the fair coin, what is the probability of getting more than 2 heads? Given that I choose the biased coin, what is the probability of getting more than 2 heads? That means, a kind of conditional probability comes into picture out there, right. So, we are going to look at this. So, what we do is, in this case, so in such a scenario, it is convenient to define conditional probability or conditional, in this case we are going to look at conditional probability mass function. Let us say P x of k given fair coin and P x of k given biased coin, right. This is what we have. And what is interesting, you are tossing the coin 5 times and you are asking for probability of getting more than 2 heads. Therefore, that distribution of number of heads after having chosen the coin is going to be binomial distribution, is that right. So, what we are going to say is, we are going to say that the conditional PMF is binomial whose probability value P, whose value of P or whose value of P depends on the coin that is chosen. Coin chosen and k is the number of heads. Right. Okay. So, therefore, what I have is, I have probability, I have to look at P x of k, which is nothing but the probability of getting k heads. This is given by probability mass function of k, given that you chose a fair coin, into probability of fair coin plus probability of k given biased coin into probability of biased coin. Right. Oh, we have seen this somewhere else. What is that? Where did we see something like this? They said Px of k is equal to Px of k given fair coin into P of fair coin plus Px of k given biased coin into P of biased coin. Where did we see this? Well, this is actually the law of total probability which we saw when we did Bayes theorem. So, this is basically the law of total probability. So, we have this is basically the law of total probability. Right. So, that is what we have. So, let us look at what is the problem we have had. The problem at hand was asking for probability of x greater than or equal, or probability of k greater than or equal to 2. That means we were looking for at least 2 heads, but then this at least 2 heads will depend on the coin that you choose. So, we are going to say Px of k greater than or equal to 2 is not, or P of k greater than or equal to 2 is nothing but sigma k is equal to 2 to 4 Px of k, right. This is sigma k is equal to 2 to 4 Px of k, which is nothing but sigma k is equal to 2 to 4 Px of k given fair coin into probability of fair coin plus Px of k given biased coin into probability of biased coin. So, the probability mass function of k greater than or equal to 2 basically depends on the conditional probability mass functions, right. It depends on the conditional probability mass function. So, what you are going to do is you are going to say that the PMF depends on the conditional PMFs. Right. So, this is what we have. Now, let us see if we can actually put it in a let us do it from the idea of event, where I am going to say the event A is nothing but getting more than 2 heads, and I am going to look at x to be the random variable associated with the coin chosen and y to be the number of heads, right. So, I am going to do something like this. So, what I have is I am going to define something like this. Let A be the event of getting more than 3 heads or more than 2 heads, and x denote the coin chosen, and y the number of heads. That means A, what are we going to say? A is the event of getting more than 2 heads. This A depends on what is the coin that you choose, and then you look at the number of heads. So, I am going to define probability of A to be equal to sigma I is equal to 1 to 2, sigma j is equal to 2 to 4 P x comma y of I comma j, where I denotes whether the coin is fair or not. You can say if the coin is fair, you put c is equal, I mean x equal to 1, and you say that if the coin is biased, you say x is equal to 2, right. So, this is what we have. That means I am going to now define my event. What is the event here? The event is going to be the following: sigma I comma j such that. So, this is going to be the set of all values I comma j such that I comma j is an element of A, right. Now, I is equal to 1, that means you choose a fair coin, j will go from 2 to 4, you get 2 heads on the fair coin, 3 heads on the fair coin, or 4 heads on the fair coin. Similarly, I is equal to 2 would say that it is a biased coin. So, j is equal to 1, 2, 3, 4 number of heads that you get. So, this basically looks something like this. So, which is given, this is nothing but probability of x equal to I comma y is equal to j, that is given by this whatever probability that we have. So, this is the probability that we are looking for, right, into, yeah. So, this is going to be p x comma y of I comma j. So, this is what we have. Therefore, now you see I am going to relate all these things. I am going to relate the joint probability mass function, I am going to relate the marginal mass function, and I am going to relate the conditional probability mass function, all of them I am going to do it. So, I am going to have p x comma y of I comma j is nothing but probability of x equal to I. Remember, I am looking at discrete random variable in this case, I am not getting into continuous yet. I mean you can actually replace this p x y with f x y and call it as a continuous distribution function or the probability density function, and p x of x equal to I and y equal to j, that is going to be a problem because point probability mass is 0, we need to look at something else. So, p of x equal to I comma y is equal to j, which is nothing but probability of y is equal to j given x equal to I into probability of x equal to I. Similarly, we also have the conditional, I mean I am going to write it as in terms of conditional probability mass function. So, I am going to write this as p of y is equal to j given x equal to I into p x of I. What is this p x of I? This is basically the marginal probability mass function, this is the marginal PMF, right. This is basically the marginal PMF. Now, something interesting happens here. What is that? We see this p of y equal to j given x equal to I, and this is a valid probability function, it is a valid probability number. Now, what do we mean by that? That means it must follow all the axioms of probability that we define. So, it says, so some of the properties what we see is we look at the following. We are going to say for a given x equal to I, we have 0 less than or equal to probability of y equal to j given x equal to 1 less than or equal to 1. It is a valid probability function. So, this inequality holds, and sigma over all j p x comma y, I should not say p x comma y, I will put it this way, I will say probability of y is equal to j given x equal to I is equal to 1. That means, you sum up all the probabilities, you are going to get 1 there, right. So, this is a very interesting notion of probability, because I mean you just fix the I, you can't vary both I and j simultaneously and say the sum adds to 1, no it is not, you choose a specific I and then you compute all the probability of y equal to j for different j given that x equal to I, that condition is met, and then you add all the probabilities, you will get 1. So, what we will do is right now now that we understood what conditional probability mass function is, let us go for formal definition of conditional probability mass function. As I said, like all these things you can do it even with your conditional I mean continuous random variable. So, what I am going to do is I am going to define the conditional probability mass function. We define the conditional PMF as P y given x. This is to denote that this is going to be a conditional probability of j given I is nothing but P x comma y of I comma j divided by the marginal mass function P x of x equal to I. This is clear. This is saying a very specific value x I y j and so on, I mean I and j and so on. Now, what I am going to do is I am just going to make a generalized version of this. I am going to say P y given x of y j given x I is equal to P x comma y of x I comma y j divided by P x of x I. Right. Now, here comes something very interesting. What is that? Let us consider the case where I had my two coins, coin 1 fair coin and the biased coin which is coin 2. Now, I have number of heads 1, 2, 3 and 4. So, this is 1, 2, 3, 4. So, if you take a coin and then you toss it, let us say 5 times or 4 times, what are we going to get? We are going to get the number of heads like this. So, let me say I am going to toss it 4 times. What I am going to do is I am going to choose the first coin I will get 1 head or 2 heads or 3 heads or 4 heads depending on the toss result or depending on the toss outcome, right. Similarly, if I take probability, this is basically the fair coin and this is basically the biased coin. So, we have this. Here again I can get 1, 2, 3 and 4, right. That means the moment you choose the first coin, that means probability of something given x is equal to 1, the number of heads in a 4 trial toss is going to be P x of x I equal to 1 given the y I is equal to 1 given that the coin chosen was the first coin, y is equal to 2 given that the coin chosen was coin 1 fair coin and so on. So, what we see is we have this, we make a very important observation here. What is that? We are going to say that the conditional probability or the conditional PMF is a family of PMFs keeping x I constant. Okay, keeping x I constant. Therefore, what are we going to do? Now, what do we mean by this? We mean to say that I am going to look at the conditional probability of y given x of, let us say j given coin 1 which corresponds to 1, right, and j is equal to 1, 2, 3, 4. Similarly, I have the conditional probability P y of x given that it is a biased coin, I have j is equal to 1 to 4. Is that clear? Now, what is interesting to see is, it is interesting to see that the conditional probability of y given x, probability mass of y given x of j given the first coin, if you add this over j, the value that you get is 1. Similarly, for the second probability mass value, I have j is equal to, let us say, minus infinity to infinity. I am now going to look at this particular coin which is biased P by x of j given 2, you sum of these values will always give you 1, right. However, what is interesting is, let us note this, however, we always have some exceptional cases like in the previous one. So, we say that however, sigma I is equal to minus infinity to infinity p x given y or p y given x of j given 2, or we want to look at j given I. So, let me put that as j given I, but I am going to do summation over I. I am going to do summation over I. That means what I am going to do is I am going to look at the biased coin and then going to look the fair coin and so on. This is never equal to 1, this need not be equal to 1. Is this clear? This is not equal to 1, is that clear? Okay. Now what you do is you can do the similar stuff in our continuous probability continuous random variable 2, where you can look at the joint probability density functions, marginal probability density functions, and then you can get the same thing. So let us quickly look at that. So if x and y are continuous random variables with joint PDF which is given by f x comma y of x comma y, right. I have this, in which case I can define f y given x of y given x is nothing but f x comma y, the joint probability mass function f x comma y divided by, I want to get f x of x, this is y given x, f x of x, and how is that obtained? This is nothing but f x comma y of x comma y divided by integral minus infinity to infinity f x comma y of x comma y dy. Right. Similarly, I can do x given y and so on. Let us quickly do that, and so I have f x given y of x given y, which is nothing but f x comma y of x comma y divided by integral minus infinity to infinity f x comma y of x comma y dx, right. These things I have. And you can see in the continuous counterpart also we had the same thing, we had to define our conditional probability. Okay, let us just put it like comparison and then see what happens. I will just put a I will list out the discrete conditional probabilities, and I will put the continuous random variables and their conditional probabilities. I will put it like this. So let us see what happens. So in case of discrete random variable, I have p y given x of let us say y j given x I is nothing but the joint probability mass function divided by summation p x comma y of x I comma y j summation over all j. Similarly, I have p x given y of x I given y j, which is given by p x comma y of x I comma y j divided by sigma over I p x comma y of x I comma y j. That is exactly along those lines what we saw in case of continuous random variable. I had f y x of y given x is nothing but f x comma y of x comma y divided by integral minus infinity to infinity f x comma y of x comma y dy, and similarly I have this f x given y of x given y is nothing but f x comma y of x comma y divided by integral minus infinity to infinity f x comma y of x comma y dx. That means if you integrate the joint probability density function with respect to x, you end up getting the marginal density function of y, and if you integrate with respect to y, you get the marginal density function of x. So that is how it is done here. But what is more interesting out of all these things is our Bayes theorem. We have done conditional probability and all those things. So the question now, that the question to ask is like, can we do our Bayes theorem here. Yes, of course we can do Bayes theorem. In fact, what we have done, let us look at the Bayes theorem for let us say the discrete random variable case, Bayes theorem. I have Bayes theorem for the discrete random variable case, which is given by probability of y given x of y j given x I is equal to p x given y of x I given y j into probability of y j, that is the marginal probability mass function, divided by summation over j. I have the same thing, p x comma y of x I given y j into p y of y j. Oh, this is exactly what our Bayes theorem was. There we studied p of a 1 or a I given b is nothing but p of b given a I into p of a I divided by summation p of a I given b or p of b given a I into p of a I. That is what we had, exactly what we have here also, right. Here also we have the same thing, and in case of continuous random variable I will write the Bayes theorem. Bayes theorem is given by f x given y or f y given x, you can put either of them. So, I do this f y given x of y given x is equal to f x given y of x given y f y of y divided by integral minus infinity to infinity f x given y of x given y into f y of y dy. So, this is precisely the Bayes theorem. So, now what we have seen is, in this lecture we have actually looked at the idea of conditioning of random variables, which is very essential when you look at machine learning, where you have multiple features and multiple classes. Your Bayes classification is all dependent on this. You of course you have your probability mass function or your density function, all those things, but your Bayesian classification is dependent on this. You know the distribution function, you know the density function, you know the prior, you know the I mean you just want to find out the posterior. Now all these things are like captured here, like what we have, and it is all based on conditioning of random variables. So, most important stuff that you see is like, especially in terms of ML, where you look at multiple features and other things to be there, multiple classes, what we are looking for is we look for conditional probabilities, and when we look for conditional probabilities, naturally we look for the probability of the joint probability and stuff. So, where we started this entire week's course material or the lectures, we started with the joint distribution of random variables, and then we went on to say, okay, joint distribution in terms of discrete random variables and in terms of continuous random variables, both we did. Then we looked for joint moments of the random variables, which we did. We looked at the idea of covariance and stuff. We said that covariance is it's an interesting metric, but with the units it has its own problems. So, we normalized it to a dimensionless quantity and called it the correlation coefficient, and then we said this correlation coefficient is going to basically measure a linear relation between the random variables, and then it kind of made us think that, look, I have this joint probability mass functions or joint probability density functions, and I also have the marginals. Therefore, it also makes sense for us to look at conditional probability mass functions and conditional probability density functions. We looked at what are conditional probability mass functions and conditional probability density functions, and how do we get to that. Basically we said conditional probability is nothing but which gives you some update about an event A upon the occurrence of event B. That means if A and B are not independent, then I am going to have some new information. That means I get an extra knowledge about the event A upon the occurrence of event B. That is exactly what we use when you look at your ML. You have these features, and these features are there. What is the probability that it belongs to this class? What is the probability that it belongs to that class? So, we are going to look at these features and say, okay, does it belong to this class? If yes, what is the probability? Does it belong to this class? What is the probability? So, we are going to look at that. And we also said, look, it is not just about conditional probability. We also have Bayes theorem, in terms of your probability mass functions and probability density functions, and that is what we have seen here. Of course, you do have conditional expectations and all. We, for the want of time, we may not do it, but if it permits, if time permits, I would probably take some 15 minutes time and then put this conditional expectations and stuff. So in this module, what we have done is we have looked at random variables which go hand in hand, which exist together. That means we were studying the joint behavior, and we looked at various other things, conditioning and joint distributions and stuff. When we come back in the new module, or in the next week's module, we are going to look at inequalities in the first place. That means, look, the cumulative distribution function was giving us probability of the random variable taking a value which is less than or equal to a. That means I want to find out, I have, suppose I set a threshold, I want to find out what is the probability of the random variable not exceeding that threshold. That is given by my cumulative distribution function. But what I am interested is not below the threshold. I might want to find out in some cases where what is the probability of the random variable taking a value beyond a threshold. And that is where we get into the idea of tail probabilities and stuff. So when we come back in the next week for our lecture, we will look at some of these inequalities, two of them which are very important, namely the Markov inequality and Chebyshev inequality, and we will also look at limit theorem, which is very essential. We are going to look at central limit theorem. We will also look at sample geometry. Can we give a geometric meaning to the sample? That means, can it be a, we have looked at vector spaces and stuff, so can I actually give a vector perspective of a sample, and in that case what do I understand? Then what we do is we look at covariance matrix and properties. That will be the agenda for the next week. Namaste.